Hello friends, in this video we are going to study about the microwave spectroscopy. The region of microwave spectroscopy in electromagnetic spectrum is 0.033 per centimeter to 3.3 per centimeter, or it can be said in meter, 3 into 10 power minus 1 meter to 3 into 10 power minus 3 meter. It is a study of rotation of the molecules, okay, and that's why we call it as rotation spectroscopy, and it gives information on molecular structure, bond lengths, dipole moments, and reduce mass. Okay, the selection rule is molecules must possess permanent dipole moment. See, for example, the molecules like carbon monoxide or HCl, they're all microwave active because they have permanent dipole moments. The molecules like H2, Cl2, they are microwave inactive because they don't have permanent dipole moment. Okay, the second selection rule is delta J is equal to plus or minus 1. Okay, the J denotes, J is rotational quantum number. Rotational quantum number. The values are J is equal to 0, 1, 2 and so on. Okay. We'll discuss about this selection rule, the second selection rule, later with some illustrations. Okay. Now let's come to this diagram. You see, this is a rotating molecule. This is an atom whose mass is m1, the other one is m2, so it's a heterodiatomic molecule. It's rotating through this rotation axis, and here is the center of mass. The internuclear distance is capital R. Let us put it as small r for convenience. The center of mass to this atom of mass m1 is equal to r1, and here the distance is, center of mass to this atom is r2. The total internuclear distance is r. So the moment of inertia I is equal to mu r squared. Okay. Moment of inertia denotes the resistance to rotational velocity. Okay. If the mass is more, the rotational velocity will be more. I mean, the resistance will be more. The internuclear distance is more, the resistance will also be more. The reduced mass mu is equal to m1 m2 divided by m1 plus m2. Okay. Let us see the energy of the rotating molecule. It comes from the quantum mechanics, the rigid diatomic rotor. Okay, rigid rotor. So the energy of the rigid rotor is equal to h squared by 8 pi squared I into j plus 1 joules. In spectroscopy, it is customary to use per centimeter instead of joules. For that, we need to divide everything by Hc. For that, to distinguish joules and per centimeter, let us use this epsilon. So h squared j plus 1 divided by Hc. Divide everything by Hc into 8 pi squared I per centimeter. Okay. So h squared, h cancelled. So that is equal to h j plus 1 divided by 8 pi squared IC per centimeter. So let us take this entire thing as B. Okay, B means rotational constant. Okay, so B j plus 1 per centimeter. Okay, that is the energy of the rigid rotor. Okay, the values of j is equal to 0, 1, 2, it keeps going. So these are the allowed values of the energy of the rigid diatomic rotor. Let us see the rotation levels. J is equal to 0, 1, 2, 3, 4, 5, it keeps going. And the energy gap, you see, it keeps increasing. We know the formula, just now we have seen energy Ej is equal to B into J plus 1 per centimeter. Okay, if J is equal to 0, E0 is equal to 0. If J is equal to 1, E1. Put J as 1 in this equation, then you will get 2B. J is equal to 2, how much? 6B. So, write everything. J is equal to 0, 0 energy. J is equal to 1, 2B. J is equal to 2, 6B. J is equal to 3, you will get 12B. J is equal to 4, 20B. J is equal to 5, 30B. These are the energy values from J is equal to 0 to 5. Okay. The energy difference, you see, here it is 2B, here it is 4B, 6B, 8B, 10B. See, energy gap increases. That is why the gap between each two successive energy levels keep on increasing. Okay. Now let's see the transitions. Let's see the first transition, 0 to 1, 0 to 1. J is equal to 0 to 1. Okay. The energy difference is for 1, 2B, for 0, 0. So the difference is 2B. 2B. The energy required for this transition 0 to 1 is 2B, and 1 to 2, because it should follow delta J is equal to plus or minus 1. Okay, so this is for plus 1, 0 to 1, 1 to 2, 2 to 3, that is allowed, isn't it? 2 to 3, 3 to 4. These are the allowed transitions following delta J is equal to plus 1. Okay, this, if you take this one 0 to 2, this is not allowed because it violates the selection rule. So these are the allowed transitions. So this one is 0 to 1, this is 1 to 2, this is 2 to 3, 3 to 4, and this is 4 to 5. Here the energy difference is 4B, here 6B, 8B, and 10B. Okay. Okay. There's a general formula to calculate this delta E. That means J to E of J plus 1, okay, is equal to, there's a general formula, 2B into J plus 1. Okay, this is a general formula for each transition following delta J is equal to plus or minus 1. Okay, right. Now we'll get the rotation spectra like this. Okay, for this line, for each transition we get a lines. Okay, for this transition another line, for this transition we get another line, and the energies you see, for 0 to 1 2B, and 1 to 2 4B transition, 4B, and 2 to 3 6B, similarly 8B, 10B. So these are the lines obtaining with these energy levels, with these energy amounts. So what is the difference? 2B and 4B, the difference is, I mean the gap is 2B, and here 4B, 6B, 2B. 6B and 8B, the difference is 2B. Here also 2B. So in the rotation spectrum, the lines, the gap between the lines is 2B. So that is what we call as frequency separation. Frequency separation. Frequency separation is equal to 2B. So pure rotation spectra of the rigid diatomic rotor, the frequency separation is 2B. Now let us see the effect of isotopic substitution. Okay, carbon monoxide, it is C12, here it is C13. Okay, the only difference is mass. Internuclear distance must be same, the only difference is the mass. Here the C13, the mass is more than C12. Okay, if the mass is more, reduced mass is also more. Okay, reduced mass for C13 is more than reduced mass of C12. Okay, to distinguish C13, C12, I put star for C13. Okay, now see this formula. Rotation constant B is equal to h by 8 pi squared IC. From this formula, you can understand that B is inversely proportional to I, right? Similarly, moment of inertia I is equal to mu r squared. From this formula, you can understand that I is directly proportional to mu. Okay, I is directly proportional to mu means mu must be inversely proportional to B. Okay, so B is inversely proportional to I and mu. Okay, if from this, if reduced mass is more, B is less. If this one is less, B is more. Okay, so in C13, reduced mass is more. That means B must be less. Okay, that's the idea we need to understand. B of C13 is less than B of C12. So now let's come to this point. Let's take B of C12 and B of C13. Star denotes C13. Okay, this is a general formula. B, this is a formula, and B star, this is another formula. Okay, B star, I star. Okay, I star corresponds to B star, C13. So you solve everything, cancel 8 pi squared, C cancel, you will get this one. I star divided by I of C13 divided by I of C12. And I is, this is a formula, no? Mu squared, I is equal to mu r squared. Okay, so R cancel, mu star divided by mu of C13 divided by mu of C12. So let me consolidate everything. B by B star is equal to I star by I is equal to mu of C13 by mu. Okay, this is the idea we need to get at last from the effect of isotopic substitution in microwave spectroscopy. Hope you understand. If you have any queries and comments, please write it in the comment box. We'll meet in the next video with some other interesting topic. In the coming video, we are going to use all these concepts and formulae in problem solving. Okay, wish you all the very best. Thank you very much.